so section 14 is on the derivatives of trig functions. So if you remember, we talked about the derivative of sine and cosine. So the derivative of sine is just plain cosine, but the derivative of cosine is negative sine. Okay, so if you know those, you're going to be good today. So number 1, so it says find the equation of the line tangent to y equals 2 sine of x plus cosine of x at 0, 1. So we've had a lot of these so far. So anytime we see find the equation of the line tangent to, some of you guys were trying to think way back to when we do it with when we found the derivative with the limit definition. We don't have to do that. Now that you know the derivative with the shortcut method, you can just use the shortcut. You don't have to do limit as h goes to 0, all that. So when I take the derivative, I'm going to do y prime equals, and I have 2 times sine of x, so its derivative is going to be 2 times cosine of x. And then the derivative of cosine is going to be negative sine of x. So we get 2 cosine of x minus sine of x, basically. Okay, so what this represents is this is the slope for any x value. Claire, are you with me? So at any x value. Okay, we want to find the equation of the tangent line at a certain x value. What x value do we have? 0. Okay, so when we plug that in, that's finding like our m in y equals mx plus b. And you can write like y prime of 0, right? So y prime of 0 would be plugging in 0, so I had to get 2 cosine of 0 minus sine of 0. And if you think about our unit circle, the cosine of 0, so 0 radians is over here on the right side, is 1. And sine of 0 is 0. So our slope then is 2. So in order to write the equation of a tangent line, we always need the slope, which we get from the derivative, and we need the point that it goes through. So do we have the point as well? Yeah, it goes through the point 0, 1, right? We were told that. If it just said at x equals 0, we would plug in that 0 into the original y value to find the point that goes with it. So we have this point and this slope. So we can do y minus y1 equals m times x, not m, sorry, 2, times x minus x1. So you can write it like this. Or if you recognize that that 0, 1 is a y-intercept, right? Like over 0 up 1 is a y-intercept, then you can just plug that in for your b in the form y equals mx plus b. So you could also have y equals 2x plus 1. But remember, it's okay to leave things like this in the AP test, like in the point slope form. Okay? All right, so we need to figure out these derivatives of our other trig functions, because we don't just have sine and cosine. We have other things, right? So we have cotangent of x. So if we're going to find the derivative of cotangent of x, what I want you to do is write it as cosine of x over sine of x. All right, so you can always get this the long way by doing the quotient rule, but our goal eventually is that you just have these memorized. There's a lot of things that you memorize in AP Calc. This is one of them. So you're going to know that the derivative of cotangent of x is going to be negative cosecant squared x every single time. Okay, so we're going to get there. So let's figure out how we can get that. So when I'm finding the derivative, y prime, I do the quotient rule. Do you guys remember what it starts with? Low d high minus high d low, all over the square root below. So our low is sine of x. D high is the derivative of cosine, which is negative sine, minus high is cosine of x. D low is going to be cosine of x, all over the square of what's below. So sine squared x. Or you could write sine of x in parentheses squared. It is not sine of x squared. Like some people write this. That is incorrect. That would be sine of, and there's an invisible parenthesis there. Do you guys see how that's different? Okay, so we start combining. So on the numerator, we have negative sine squared x minus cosine squared x. What do we think that works out to be? I don't know. What do you think? Like you could break it into, like you could be like, oh, it's negative 1 minus cotangent squared. Is that what you're saying? Like breaking sine squared into both pieces? You could do that. But there's an easier way.
Sine square of x.
Yeah, do you guys see this combines? Like if I pulled out a negative 1, maybe I should show that step. If I pull out a negative 1, what do I have? That Pythagorean identity, right? Sine squared plus cosine squared all over sine squared. So I get negative 1 over sine squared, which ends up being negative cosecant squared x. So that's a lot of work to do, right, to get here. Could we maybe just memorize that the derivative of cotangent of x is negative cosecant squared x? Yeah, especially after you do that a few times. You're like, oh, I just got this. I know how to do this. All right, so I always talk about when I was I don't know, I was like a freshman in college. I decided I was going to work at a tutoring center, and I went in and I had to take a test that tested my knowledge of like, I think I was older. I must have been like a junior because it had been a while since I'd taken Calc 1. And I decided I had to take some kind of test that tested my knowledge of like pre-calc, algebra 2 stuff, and AP Calc stuff. And I remember taking this test for AP Calc, or for calculus, and after I was done, they were like, wow, you did really well. You got a perfect score on this test. We've never had someone come in and get a perfect score because they always forget those trig derivatives. And I was like, oh, well, I just did them off to the side and did like the quotient rule because I'd forgotten them. So if you ever forget them, you can do this. And I put this on the test sometimes. So I'll say, find the derivative of cotangent of x as if you had forgotten what it was, like if you only use the quotient rule with cosine and sine. So you guys can do that, right? So let's do this on the next one. So if I have secant of x, I would first rewrite that as 1 divided by cosine of x, right? So we do y prime equals, and we're going to do our low d high minus high d low all over the square of what's below. So our low is cosine of x. D high, the derivative of 1 is just 0. Minus high is 1, d low is negative sine of x. All over the square of what's below, all over cosine squared x. Okay. So we end up getting a positive sine of x over cosine squared x. So here's how I want you to break it up. I want you to think of 1 over cosine of x and then sine over cosine of x. Do you guys see how that's the same? Like I can break the sine over cosine squared if I multiply it back in. So I'm just breaking apart our fraction into 2 separate fractions. Okay, do you remember what 1 over cosine is? Secant x. What about sine over cosine? Tangent. So the derivative of secant is secant x tangent x. All right, so same idea for cosecant. So cosecant is 1 over sine. So we follow the same process. So we do y prime equals, and we do our low d high minus high d low. So we do low is sine of x, d high is 0, minus high, d low, derivative of sine is cosine, all over the square of what's below, so all over sine squared x. So now we get negative cosine of x over sine squared x. So we're going to kind of break it up the same way. So I'm going to have a negative 1 over sine of x times a cosine of x over sine of x. So I broke it apart into 2 fractions just so I can write it as 1 on one line. It's easiest for us to type math things on one line, so if we can make it a single line, that's easier. All right, so I'm going to have negative 1 over sine of x. What's that? Negative cosecant of x. And then cosine over, I just said it, over sine is cotangent. I do that all the time where I start to say something. So the derivative of cosecant x is negative cosecant x cotangent x. So there's a bit of a pattern to these. So here's how it goes. So the derivative of sine was cosine, and the derivative of cosine was negative sine. Okay, sine and cosine are what we call cofunctions. I don't know if you guys remember from pre-calc, but basically they're the same shape. Like sine looks like this, and cosine's just been shifted a little bit. So their derivatives are very similar. They're going to be cofunctions of each other. Do you guys see that? So same with tangent and cotangent. Those are cofunctions of each other. So if you think about tangent and cotangent, they're like this. But then one of them is going to be shifted over by pi over 2. Right? So you could find both of those. Okay, their derivatives are going to be similar as well. So the derivative for tangent, do you guys remember that? It's been a while. Secant squared. Yeah. Tommy knew it. Tommy got it on his quiz too. He was like, I'm not doing any of this work. I'm just going to write secant squared. He knew it. All right, so this one's going to be similar to it. It's going to be basically a cofunction of it. It's going to be shifted. So it ends up being negative cosecant squared. So we gained a negative in the co-function. Okay. Same with cosecant and secant. So we just saw that secant was secant x tangent x for its derivative. So its friend, its co-function, is going to be very similar, but it's going to be the cos. So it's going to be cosecant x, cotangent x, and then it's negative. Okay, and you can play around with the graphs of those and you can see why that's true. But basically, if you pair them and you're like thinking of these two together, and these two together, it's a lot easier. So I always tell my students that for the sine and cosine, I think you guys memorize those. It's not a big deal. You remember those. But these ones, the tangent and cotangent, you gain a negative and a co for the cofunction, right? And you gain a negative and a co for the cofunction. That's a little confusing with the sine and cosine, though. I don't want to say you gain a negative and a co, because then people are like, oh, so the derivative of, well, I guess it's kind of the cosine. What's the cofunction of cosine is sine. It's a negative and co as well. All right, so I said whenever I forgot one of these derivatives, I always just use the quotient rule or product rule or whatever, so quotient rule in this case, with the derivatives of sine and cosine. But it's best to memorize these because you don't want to waste a ton of time doing all that on your AP test when time is limited as it is, okay? So how about the 30th derivative? Ooh. So if we have y equals sine of x, can we keep going through the derivatives until we get to the 30th one? All right, so how about y prime? What's y prime? Cosine. Y double prime. Derivative of cosine is negative sine. Y triple prime. Yeah, so it's negative and the derivative of sine is cosine, so negative cosine. All right, so y, and then the fourth derivative. So we stopped doing this after a while because we don't want to do this for the 30th derivative. That's a little crazy. So once we get to 4, we write it as a parenthesis and a 4. So that way we know it's not y to the 4th, but it's y, the 4th derivative of y is what that represents. So that was going to be
Sine.
back to sine, okay? So then the 5th derivative would be cosine, and it continues that pattern. When does it start again at sine? 8 is sine. Right? 6, 7, 8.
Cosine for 30.
So it's 12, 16. What are we doing? We're doing power, or not powers, multiples of 4. So the 28th is sine. So the 29th is cosine. And the 30th is negative sine. Does that make sense? So you can kind of see a pattern with those. They start repeating. All right, so number 2, so differentiate cosine of x over 2 plus sine of x. For what values of x does the graph of f have a horizontal tangent? So these are calculus keywords, horizontal tangent. What do we know? The slope equals 0. So we can write f prime of x equals 0, or you can write m equals 0, or whatever you want. So we want to find the derivative, and we want to find when it's equal to 0. So again, we're doing quotient rule, right? We're doing low d high minus high d low. We can't simplify this one. Like some people are like, oh, can I write like cosine of x over 2 plus cosine of x over sine of x? Why can I not write that? So I can't write cosine of x over 2 plus cosine of x over sine of x. Do you guys know why we can't do that? I don't know if I understand what you just said. I think you're right, but I don't know. Yeah.
It doesn't work because like they don't have common denominators.
Yeah, they don't have common denominators. You couldn't combine them, right? It only works when there's like a single term down here, like one thing not separated with like pluses or minuses. If you think about numbers, like if I had 1/2 plus 1/3, that's not the same as 1 over 2 plus 3, right? 1/2 plus 1/3 is much bigger than 1/5. It doesn't work that way. So we can't combine, or we can't break it down, so we have to do that quotient rule. So we're going to do low is 2 plus sine of x, and put it in parentheses. And then we multiply by the derivative of the high, which is negative sine of x, minus high is cosine of x, and the derivative of low. So what's the derivative of the denominator? Just cosine of x, right? Because the derivative of 2 went away. All over the square of what's below, so 2 plus sine of x, squared. So if we want a fraction, this is a big fraction, to equal 0, so if we want all of this to equal 0, what am I setting equal to 0, the numerator or denominator? The numerator, right? It's kind of like you can take this, like, this part over here and multiply it over and it goes away. Like, we're not worried about the bottom. We're worried about the top. Really, the only bad thing would be if it's like a whole, if you could factor it out, we would look for that, but that's fine. So we want to set our numerator equal to 0. So what is our numerator? So I'm going to distribute in. So I'm going to have negative 2 sine of x minus sine squared of x minus cosine squared x. And this is all going to equal 0. So I don't need to write the denominator. What do we notice? You're right, Grace. I know you know. Are you looking here?
Yeah. Is that negative 1?
It is negative 1. Do you guys see that? So we're going to have negative 2 sine of x minus 1 equals 0. And we just solve it out. So I'm going to add the 1 over, and then I divide by negative 2, so I get negative 1/2 equals sine of x. And I want to know where it works out to be, where sine is negative 1/2. So on the unit circle, sine is negative 1/2 in 2 locations. So below the axis, so in the 3rd and 4th quadrants. Do you guys remember what those numbers are?
7 pi over 6 and 11.
Ah, yes. 7 pi over 6 and 11 pi over 6. It's fresh in his mind because he did summer pre-calc. Is it fresh in your minds as well? We did it at the beginning of the year.
Would it be like plus 2 pi?
Yeah, so that brings up an interesting point. Did I say on the interval 0 to 2 pi? No. So yeah, we got to do that plus 2 pi k thing, don't we? So we're going to say for what values of x, it's going to be x equals 7 pi over 6 plus every rotation around the unit circle. So we're going to do plus 2 pi k. And then we're going to say 11 pi over 6 plus 2 pi k. So there's no way to like combine those nicely. Like sometimes when it's just like tangent, you can be like, oh, I'm not going to add 2 pi, I'm just going to add pi. Like it'd be like pi over 4 and 5 pi over 4. Well, it's just like pi over 4 plus pi k you could do. But in this case, we can't combine those, so we leave them separate. Does that make sense? Remember this? All right. All right, so number 3 is to find the equation of the tangent to the curve at the point pi over 3 comma 2 pi over 3. So we're going to plug in. Oh, well, we're going to find the derivative first. So f prime of x equals, and you guys recognize that you have to do the product rule here. Like, we don't know a rule to just take the derivative of x secant x altogether. Okay, these are separate functions. We know the rule for taking the derivative of x, and we know the rule for taking the derivative of secant of x. Okay, together we don't know the rule. We have to do the product rule. So we're going to do our first is x times the derivative of secant x. Do you guys know it yet? Secant x tangent x plus the derivative of x is 1 times secant x. And we're finding the equation of the tangent line, so we need a point and we need the slope. Well, we have the point, so we need our slope. So we're going to plug in the x value of pi over 3 in order to find it. It's going to be a little gross, because we have pi over 3 times secant of pi over 3 times tangent of pi over 3 plus secant of pi over 3. So if you had your calculator, this is where I would pull out the calculator and I would just round to 3 decimals because the AP test lets you round to 3 decimals. So you could do that, but if this was on the non-calculator section, it takes a little bit more work. Okay, so let's think about where pi over 3 is. So pi over 3 is right here. What point is associated with it? Over how much, up how much? 1/2 up root 3 over 2, exactly. So when I talk about secant, I have the reciprocal of cosine. So secant of pi over 3 is the same as 1 over cosine of pi over 3. Yeah, so it ends up being 2 because it's 1 divided by 1/2. It's the reciprocal of 1/2. So we have pi over 3 times 2, and then we got this nasty tangent of pi over 3. I always hated this one. So tangent of pi over 3 is root 3 over 2 divided by 1/2. So you can multiply by 2 over 1 and then reduce out the 2's. What do we get? root 3. So the easiest thing to do in this situation is to think about multiplying by 2 over 2 and then canceling together. So we get root 3 over 1, which is just root 3. So we have root 3. And then this is going to be, what, 2? So we get the lovely 2 root 3 times pi all over 3 plus 2. That's our slope. That's really gross, isn't it? Why? So when we put it together, it's going to look like y minus 2 pi over 3 equals this lovely slope 2 root 3 pi over 3 plus 2 times x minus pi over 3. That's what the equation of the line is, and we just leave it. It would probably be a calculator one. You'd probably be allowed to round. Whenever there's like pi's and square roots, it's okay. All right, so number 4. So an elastic band is hung on a hook, and its mass is hung on the lower end of the hook. Are you guys in like physics right now? Do you do these problems? So you have this like little hook, and then you have this like rubber band, and then you got some kind of weight on the end of it. Okay, so you're gonna pull that weight down, and when you let go, that rubber band has some like tension in it, and it's gonna go up and down, up and down, up and down, up and down. It's gonna vibrate. Okay. So when something like that happens, it's a sinusoidal function. That's what we call them, sinusoidal function. It means it involves sine and cosine. Okay, so it makes it like a wave. There's lots of things that make waves in real life. All right, so the equation of the motion ends up being, it's probably not this simple, but it's going to be S equals -2 sine of t plus 5. I apologize in advance because my S's and 5's always look the same, so I'll try really hard. Sometimes for my S's, I write them as a lowercase cursive s. Do you guys know what that is? Like that. I know you guys don't have to take cursive anymore. So, all right, so when I find the velocity and the acceleration, this is actually in the previous section, maybe I shouldn't have skipped. Think about like position. So our position function, which is in S, would be things like a distance. It'd be like feet, miles, meters. Those would be the units. Velocity is going to be like miles per hour, right? Feet per second, meters per second, right? It's a derivative. It's a slope. It's a rate of change. Does that make sense? You take your previous one and you're finding its rate. Do you guys know what I'm saying? So if I want to find the velocity, what I do is I take the derivative of s. So velocity is s prime. So the position function's derivative. So when I do, I get -2 cosine of t, cosine of t, and then plus 0, because the derivative of 5 goes away. And then my acceleration, well, that's going to be like feet per second, miles per hour. Well, we don't often say feet per second. What do we say? Feet per second squared. That's an acceleration. Okay, so these are all related to one another. So it's the rate of change of the velocity function. But the velocity function was the rate of change of the position function. So it ends up being the second derivative of the position function. So it's going to be s double prime, which is -2 times negative sine of t, which is the same as 2 sine of t. So those are our velocity and acceleration functions after t seconds. So it says, well, when is the speed the greatest? Okay, speed is related to velocity. So if you guys take physics, you'll talk about this a lot. Like velocity can be negative. Like I can talk about walking -4 feet per second. Okay, I can do that. What does that mean? I'm walking backwards. It has a direction to it. So if I'm walking forward, my velocity is positive. If I'm walking backwards, it's negative. Speed is always positive. So if I'm walking backwards, my speed would still be positive. Okay, it's going to be the absolute value of velocity. So it says, when is the speed the greatest? And speed is the absolute value of velocity. Well, you could just graph that. Let's try that. So if I graph it on my calculator, so go ahead and get your calculator out. We're asking for when the speed, so speed is the absolute value of velocity, is the greatest. So we could just graph the speed by doing math, number, absolute value. Did you guys see how I got that? So I got ABS up there. So I hit math, and then I arrowed to number, and then I hit absolute value. So I get ABS, And I'm going to put in the velocity function. So negative 2 cosine of t. So negative 2 cosine of t. Just make sure your calculator, so you might want to hit mode. Make sure yours is not in degree mode, it's in radians before you hit enter. All right, so when I hit graph, it's going to give me something that's always positive. It's always above the axis. Do you see it? Isn't it cute? So if I want to find when the speed is greatest, I would find all of those maximums. And I'd be like, oh, at t equals whatever. Right? So I can do a second trace, and I could find it. The first one looks like it's at 0. Let's figure out how far away they are from each other. So I'm going to do maximum, number 4. And I'm going to go over to this next maximum. So I'm going to hit enter, enter again, enter. And I end up getting 3.141591. What do you think that is? Pi. Do you think it's every pi? I think it's every pi. Do you guys see how it's kind of symmetric? Okay, so the speed is the greatest when that absolute value of negative 2 cosine of t is maximized, right? And we did that, and we found it was at t equals 0, pi, 2 pi, and so on. So we're going to write 0 plus pi k, or we could say pi k, right?
But would it slow down?
Would it slow down? It would eventually slow down. So what causes it to slow down? Like things like friction and so on. So we're ignoring friction. I'll often write that in my story problems, ignoring friction and air resistance. All right, that's the hard part with physics. You actually have to consider a lot more things. So if you're like parachuting and trying to hit a target or something, I don't know, a human cannonball, if you're launching yourself out of a cannon and trying to figure out where you should put like the mat, you should probably know physics, not just calculus. They go hand in hand. All right, so that's one way you can do it. Well, you could also, if you think about where something is maximized, think about a maximized or minimized. If I want to find like the minimum of a parabola, do you guys remember how we did like negative b over 2a in algebra 2? That's from calculus. Okay, what you're doing is you're finding when your derivative is equal to 0. What if you had an equation that looked like ax squared plus bx plus c, and you took the derivative? What do you get when you do the derivative? 2ax plus b. What if you set it equal to 0 and solve for x? You get negative b over 2a equals x, right? That's finding a maximum or minimum. That came from calculus, that equation that you used all the time in algebra 2 and pre-calc. Okay, so if I really wanted to find this by hand, what I would do is I would take the velocity function, and I would find when I'm not finding when the, I want to find where the speed is the greatest. So I want to find when its derivative is equal to 0. Okay, and what that would do is you would have your velocity function, which is negative 2 cosine of t. So it's going to look like this. It would find this number, this number, this number, this number. It would find all of those. Those are 0, pi, 2 pi, 3 pi. It would find all those maximums and minimums. Does that make sense? Actually, hang on. I did that wrong. You would find when it equals 0. This would be, dang it. I didn't do the, I graphed negative 2 cosine of t. That would be the velocity function there. So that would be at 0, pi, 2 pi, 3 pi. But when you graph its derivative, all of those locations would be where you cross the axis. So it would be at 0 pi, so it would be increasing. So it would look something like this. So you'd find all the places where it's equal to 0. Okay, so we'll do more of that later. All right, is that the last one?